Good morning and welcome. Today is Phototherapy Day. I hope that you are all excited for today. Today is going to be your opportunity to learn a lot, but also you're going to have a lot of fun working in teams, working on your lab. And we have an amazing presenter today. Miss Erin New is here. She's going to lead us for the entire day. So she's going to be here through the whole day to help you through the process. Just again, don't forget, we love student engagement. Do not hesitate to type a comment or question in chat for our presenters. And I'm going to stop speaking and let Miss Erinu take it away for our phototherapy introduction.
All right. Good morning, everyone. Hope you're all really excited to get into today. We're going to talk about, some phototherapy. It's going to be really exciting. So I'm just going to share my screen. All righty. So just a little bit before we get into everything. In general, phototherapy is the use of light in order to treat some sort of condition, okay? So that's just a little bit of understanding of what we're going to get into today. But first, just so you know who, is like talking to you throughout the day, I'm going to give a little bit of background about myself. So when I was in elementary school, we got into this whole section of physiology and anatomy. And I was always really enamored by the cardiovascular system. And especially because my area of the United States, as you can see in the map, is like significantly impacted by cardiovascular disease. And I have like a personal connection with cardiovascular disease. So it really inspired me to go into, some sort of medical field that is centered around, caring for the heart and like helping patients. And originally I really wanted to go into the medical field and be a doctor. But then when I was in high school, one of my high school teachers was actually talking about research that was being done at Duke University. And what they were doing with this research was they were actually taking the polio virus and they were modifying it and utilizing it to treat this very dangerous brain tumor called glioblastoma. And the survival rate of this brain tumor is like 7%. It's very, very deadly. And so I was really enamored by it because I thought it was like, oh, this is the most creative solution. I really want to get into research and do stuff like this. And it really inspired me to actually go into engineering. So right before college, I decided to go into chemical engineering. I graduated at the University of Notre Dame with a bachelor's in chemical and biomolecular engineering in 2022. And now I'm a PhD student at Boston University in biomedical engineering. So this is a little bit of work that I've done. So on the left, you can actually see these are lymphatic vessels, which is a type of vessel that's in the body. And they're actually sprouting within this like little jello-like substance called a hydrogel, which essentially acts like the surrounding areas around a cell called the extracellular matrix. And what I'm currently working on is kind of bouncing off this idea. And it's essentially looking at how can we actually take what is done in the human body, these different patterns and everything that arises from these combinations and patterns of chemicals to actually grow organs and actually make organs to solve the organ transplant problem because there's a very strong shortage of organs, or even like in my case, like maybe coming up with like growing a heart in essence to, help people that need heart transplants that are affected by cardiovascular disease. So that's a little bit about me. So now I kind of want to hear a little bit about you all. So here's a Slido. It's almost Halloween. So I figured what better thing to ask to get to know you all is, what is the best Halloween candy? So you all can, scan the QR on your screen and you can answer that way. You can also answer in the chat. You can also put in the code, but I just want to hear from you all. What are your thoughts? I'm sure this is like a very strong debate because some people feel very strongly about what is the best Halloween candy. You can also put the answer in chat as well in the Zoom chat if you are unable to. I think my favorite Halloween candy was always Hershey's. Ooh, Twix is coming out strong. It's very, very good. Yeah, in my high school when I was a kid, Twix was very, very popular. Got some Sour Patch Kids. Okay, that one's now pretty strong. And Reese's Cups. Snickers, Skittles, very good. I haven't heard of Mr. Beast Feastables. That must be new. Candy corn. Now, see, that's a very controversial opinion because some people are like, candy corn is really, really gross. So I was like, good for you. Yeah, these are some really great answers, guys. Milky Way. Nice. Alrighty, so I'm going to get into the presentation now, and we're going to talk a little bit about some phototherapy. All right, So just a little background. So an outline of what we're going to do today is we're going to talk about Grover's disease. We're going to talk a little bit about light and its effects on the immune system. And this is all going to try to set you up to essentially build a model and collect data to answer the question, what time is required to treat Grover's disease with blue light therapy? Okay. So with this, you have to utilize the engineering design process. So with the engineering design process, you have to first come up with an idea, and then you have to design, build, and test it. So a good example of this is actually based on this image I have on the slide, which is actually something I recently learned about, which is a soft robotics dragonfly that essentially reacts to environmental conditions. And this is a really good example of coming up with an idea, because the researcher that actually came up with this idea was just sitting in an airport, and she was just looking at planes, and she's like, you know, it'd be really cool. What if I came up with a robot that senses environmental conditions to actually guide which direction it goes in? And so you can get to ideas from basically anywhere. But for the most part, with an idea, when it comes to engineering, you really want to meet an unmet need and have a big problem that you want to solve. Because what is a solution if you don't have a problem? So that's the first thing you got to do. And then after that, you got to do research and learn about the area, like what treatments are actually, going into it right now, and what are some areas that need to be improved in those areas. And then you got to figure out, how do I want to design? How do I want to build this? And how do I want to test it to make sure that it meets the specifications that I want? So specifically for today, how would you use the engineering design process to develop a treatment for Grover's disease? All right. So your weapons for this lab, you're going to do a blue light flashlight. You're going to have a photochromatic sticker. You're going to have some brown paper and some good old AAA batteries to accomplish this task. All right. But before we get into that, we're going to go through the engineering design process for the lab and get a sense of stepping through it for Grover's disease. So step one, we got to define the problem. So defining the problem. The problem is develop a treatment for Grover's disease using blue light therapy. Okay. So we know what to solve. And the process we're going to use is the engineering design process to develop a solution. Okay. So the next steps is, after getting this problem, we got to research about it. We got to learn more about what we're going to solve and figure out, okay, what is out there? What do I need to actually figure out, and go from there? Okay. So let's learn a little bit about Grover's disease. Okay. It's a transient skin disorder that consists of a rash on the chest and the back. The target population for this, which is really important with this translational engineering and kind of developing a solution that can be utilized in patients, is typically males, and they're usually at least 40 years old. The disease recedes at its own pace, and it's usually worse in the winter months. However, a big challenge with it is there's no known cause to this, and there's also no effective treatment for it, as well as there's no exact cure. And the difference between a treatment and a cure is a cure will get rid of it entirely, whereas a treatment usually will keep the symptoms at bay for the most part. Okay, so now we know all about the disease. So what is the current treatments that are being utilized, and how can we maybe improve upon them? So the first thing that people utilize are steroid creams and antihistamines. But the problem with this, right, it relieves the symptoms of itching, which is always great because nobody really wants to be, itching all day. But the problem is it only treats the symptoms. So you're not actually getting rid of the root problem of the rash, and you're also not getting through to the underlying cause, right, because we don't know what the cause is. Then you could get into natural sunlight, and vitamin D3 as a potential option, which, helps in small amounts, but there's quite a few cons associated with this. First of all, if you're out in the sun a lot, you could get, UV skin cancer concerns, as well as what's interesting about Grover's disease is if you're exposed to too much UV light, you can actually make the condition worse. Also, when it comes to natural sunlight, right? When it comes to that, you have to utilize limited sunlight in the winter, so you don't have access to as much sunlight necessarily, especially depending on what area in the United States you live in during the winters, or even in the world. And then in some cases, when it comes to vitamin D3, you have to require constant monitoring, because sometimes taking vitamin D3 in large amounts can be a big problem. So I see a question in the chat. May I ask what the engineering problem is? So the engineering problem in this case is you're trying to solve you're essentially trying to figure out, okay, what is a better treatment for Grover's disease? What is a treatment that essentially treats the underlying problem? Okay. So in general, more generally, it's any sort of problem you want to solve. So let's say with cardiovascular disease, maybe I want to solve like with some of these cholesterol drugs that are really like cholesterol is known to be a big deal with cardiovascular disease. Maybe my engineering problem is, can I solve this element to cardiovascular disease to help patients? So that's generally what the engineering problem is. Okay, so with previous research, you always want to look at, okay, what is the background that current research have essentially come up with? And what do they actually believe are like the causes, and how can we actually utilize that background information to come up with new treatments? So researchers hypothesize that potentially the immune system is heavily involved in Grover's disease. So we're going to utilize that information to come up with a potential treatment. So just a little bit about the immune response. So there's a part of the body called the thymus gland. It's really important because it's essentially one of the main centers for directing, response to bacteria, viruses, and inflammation. A big part of it is that it's stimulated by light. And the reason being is the thymus gland is actually the center of the immune response. Reason being, there's a really important immune cell called a T cell. So you got T cells and you got B cells. T cells get their names because they actually mature in the thymus gland. And the T cells are actually the big, heavy guns and fighters in like any immune response. They're the ones that actually go in and like really effectively kill. So with sunlight specifically, it's been demonstrated that it increases the efficiency of our T cells, specifically like by a factor of 7 or 8, which is quite a lot. And more specifically, they've been looking at the fact that the blue light wavelength is a light that stimulates this response. So it's not just all light, it's just specifically the wavelength of light that makes blue light. Now, let's get into a little bit more about light specifically, because I'm sure like if you're like, wait, all light, there's different colors of light. So let's get into that a little bit. So what is sunlight? So sunlight is a mixture of electromagnetic waves. So if you've taken, some basic physics, you may have seen this, but essentially there is some very fancy spectrum called the electromagnetic spectrum. It ranges from radio waves, which, are just the waves that essentially are really proper for like sending signals. Like if you have like, a radio antenna and it's sending a signal to your car to get you to like listen to music, that's a radio wave, all the way up to gamma waves, which are really, really known for like, creating the Incredible Hulk. So very dangerous. But in between there, you have infrared rays and UV light, and that's where sunlight lies. And then essentially these range from 100 to 700 nanometers. Now, what this means is when it comes to light, it's actually expressed as a wave. So if you've taken any sort of mathematics course where you've seen like sine or cosine like expressed as a wave, it's essentially like a graph of light. So it's very similar to looking at it that fashion. If you haven't, just imagine like, a bunch of like essentially just a wave, right? Just going up and down, and all the waves are essentially the same height. So the peaks of the valley are exactly the same. And the wavelength specifically is going from one entire wave to another wave, and that is the wavelength. So you can have them be very far apart, which is where you get like the 700 nanometers, or you can get them really close together, which is the 100 nanometers. When you have them really scrunched together, where it's kind of like this really quickly, essentially that has a lot of energy because it has a very high frequency. And that's where you start to get into like the ultraviolet range. So with the wavelengths of light, they have different effects on the body, as we were talking about. So one of them is being blue light. So blue light, specifically where it gets its name, is the visible light spectrum actually is where we get color. So when you have sunlight, right, what you're getting from like what we're perceiving is actually the reflection of light off of objects. So that's what gives us color. So blue light is actually the reflection of light that we usually see. So, but the only problem here is that it only makes up 7.8% of natural light. So it's not like, that much of it. So when you're out in the sun all day, like you're not really getting that much, and that might not be very beneficial towards Grover's disease patients. So that's something to keep in mind. So how do we actually calculate the irradiance that is really associated with the light that's coming, that we're essentially absorbing, right? So energy from the sun is specifically a form of radiant energy, and it's measured as a unit called a radiance. Now, a radiance is also known as a flux. A flux is really important in engineering, and it can be also very complicated as well. But in general, all you need to know is that it's just a flow over a unit area. So how much of radiant energy is flowing through a surface of this area. Specifically, their radiance, right, is different depending on the day of the year, the time of the year, because of the way that the sun hits the surface of the earth, right? Sometimes, like, for example, you're not going to have as much sun in the winter months as you are like in the summer months. So you got to keep that in mind. And something that really helps us with that is using reference tables. So reference tables are really helpful in engineering and giving us all the background information we need to actually solve problems. So then like other research will go out in the field and do all these calculations. So then we don't have to do them over and over and over again. So they just send out these reference tables for us to look at to make these calculations. So the formula you're going to be utilizing today is essentially looking at the sun's irradiance times the area of exposure times the duration of exposure, and that'll give you the absorption. So a good example is over here. And essentially with this, it's like, okay, you have a roof that's 15 by 10. And we're going to assume it's June 15th. So we're going to use our reference table and we're going to see, okay, the irradiance is 1060 watts per meter squared. And then we're going to say it's exposed for 10 hours. And then you get your like value for irradiation or irradiance absorption. Okay. So something else that's really important with translational engineering specifically is you always want to make sure that you're understanding your patient population and what they're doing and what they're going through, and especially listening to them to get some ideas on how to solve your problems, as well as getting an idea of, okay, is this treatment actually going to be effective for this patient? Because sometimes, like, there's a lot of heterogeneity between all of us people, right? Because we're all very different people. We have different like immune systems and the like. So you always want to make sure that you are actually targeting like the right patient population with your treatment and making sure that you have the right patient to utilize it with. So for example, in this case, we're actually going to utilize a clinical observation for our lab today. So what we're looking at here is you have a patient that is suffering from Grover's disease seasonally, specifically during the winter months, but they figured out that during the summer months, while the patient plays golf a lot, they have, their symptoms subside substantially. And you ask them, okay, well, how long do you play golf for? And they go, oh, well, I play for about 5 hours during the midday sun. And it's like, oh, cool. So what if I come up with a treatment that actually tries to give the same amount of light within that time frame, but like maybe shorter. So like the same amount of radiance that allows for the same amount of radiance exposure, but like in a smaller time frame. Okay. And that's where you're going to design your solution around. Okay. So something that's really important here is going into this like formula that I was talking about a little bit earlier. And with this specifically, always in engineering, you have to make assumptions, right? Because sometimes like there's a lot of unknowns associated that maybe like we just cannot calculate certain things. So you always have to assume certain values in order to get to your solution, okay? Sometimes they can be really bad assumptions, but you always want to try to make the best assumption possible to make your solution very, very good, okay? So in this case, we're going to assume that the sun's irradiance is going to be June 15th, okay? So we're going to have 1060 watts per meter squared. That's the value we're going to utilize throughout this. In general, the sun will change, right, depending on the day of the year, but that's just the value we're going to assume for this case, all right? Area of exposure. So naturally, each person is of a different size. Every person has like, different coverage, but we're going to assume in this case 2 meters squared, okay? And then the duration of exposure based on our patient information is going to be 5 hours. So we want to target an absorption of 10,600 watt hours, okay? However, we only want blue light, right? So now we got to multiply that by 7.8%, okay? So the actual absorption that we're getting for our patient that we want to target is 825 watts per hour. However, in addition, you have to think about, okay, when the patient is playing golf, they're probably blocked by clothes. It's like, summer, it's hot. They might be, under a shade tree, chilling for a little bit, trying to cool off. So we're gonna assume from that value specifically that only 5% of the light is actually truly absorbed. So your radiance goal for the treatment is actually going to be 41 watt hours. Okay, so that's the target goal we want to reach. So on top of that note, what other variables do you think should also be considered when designing and building the solution? There's quite a few, and this is a really tricky question. So I just want you to give it a good old try. And if you don't know, that's also okay. But in general, so you obviously know that you want to have the irradiance, like you have the target goal, but what are some other variables do you think are really important in considering this? And you can think about, the patient specifically, like how would the patient react with the treatment? What are some deals with, The actual building of the device, like what are your thoughts? Cost. Yes, that is a very, very good one. Yes, cost is really, really important, right? Because you don't want to have, this extreme cost of a device because then it really impacts, the patients. Efficiency with time. Yes, time is really, really important, right? Because think about like your patient population, right? If you want to try to be, broad with these patients, right? Maybe one patient can't sit still for a long period of time. So maybe you want to have it shorter, okay? Changes in weather. Yes, changes in weather is really important, right? Because maybe like utilizing this assumption, right? Maybe it's not actually working out. Cloud cover, very good. Medical history, age and treatments. Yes, that's also very important. Yes. Good job, guys. These are some really, really good answers. Alrighty. So I'm going to get into what specifically we're going to be looking at for ours, and we're going to go from there, all right? So for this specifically, we're going to look at the wattage of light, the distance, and the residence time, okay? And we're going to utilize this to attempt to replicate the sun's ability to supercharge the T cells, okay? We're going to provide a level of energy that is absorbed, that is equal to this value that we calculated earlier, okay? So 41 watt hours. We're going to use a light wavelength that's in the blue light range. So we're going to use 410 to 490, okay? So from there, your task specifically is you're going to first measure the blue light irradiance 3 times at different distances, okay? So because I mentioned previously, distance is really, really important. It's one of the ones you want to get at because if you're trying to get at with like light therapy, it's like how close should the light be to the patient? Like what is its area of coverage it should be involved with? That should be really important, okay? And then you will also measure the area of irradiance, which is what I was saying earlier. And then you have to also keep in mind the time and the cost, right? So going back to, you don't want it to be too expensive for both like treatment centers as well as for patients, and also time, because like I was saying earlier, sometimes you have patients that can't stay like in certain places for very long periods of time, okay? Okay, so how to evaluate the blue light radiance from your lamp. So you're gonna expose the paper for 10 seconds and you have to count slowly. So don't be like, really fast to go 1, 2, 3, 4, 5, 6, 7, 8. Don't do that. So just count like 1 Mississippi, 2 Mississippi. And then after that, match the shade of red associated with the, color scale, okay? And you're gonna record these 3 irradiation values that you find in these boxes, okay? And a really big important point is don't shine the blue light in your eyes as it can cause damage. It's very important in science at all times to be safe and not actually, hurt yourselves. It's very important in like all aspects. Like when I work in lab, I always have to wear like safety gear. So just be very cautious when you are utilizing the light, okay? Okay, so while you're doing that, you have to also take into consideration the distance, okay? So you're gonna measure the area of exposure in the circle, okay? So let's say you hold it up and then you can measure the just the size of the circle in centimeters, and then you're gonna utilize this, the area of a circle equation, so pi r squared to actually calculate the area. But we want it in meters squared because in engineering and in science, you always wanna have consistent units, okay? So specifically, we're going to divide it by 10,000 to convert it over to meters squared, okay? Something that's really important to consider while going into this is the actual relationship of area irradiation to average irradiation. Now, why this is important, within this engineering, right, you always will have trade-offs, right? You want to like immediately go, well, I want to expose the whole, as much of the body to light as possible, right? But if you notice, when you go further and further from the lamp, right, your average irradiation as you go further and further from the lamp goes like down, right? So that's kind of over here. So it's going to go immediately down when you get really far away. But when you get super close, you have a smaller area of irradiation, but you're not getting as much irradiation to the patient. So there's always trade-offs in that. And you want to try to find a balance between the two, right? You want to I want to cover as much of the patient as possible, but I also want to get them the right amount of irradiation over time, okay? So that's something to consider as you're stepping through this process and considering what is the best design I want to create. And this kind of goes to some different ideas that you have to come up with, right? So with this specifically, you're going to cut out a figure and you use different colored paper to cut out circles of each area that you've measured earlier. And you're going to place them around the body as lights, right? And this goes back to, okay, well, how much of the area of the body do you want to cover all at once? And how much of it do you want to also target with how do you want to get as much irradiation to the patient as possible with these configurations, okay? And you're also going to multiply this by 2 because you want to do the front and the back. You want to make as much coverage as possible. All right. And then from here, we're going to utilize that equation we were talking about earlier, just the main equation of this whole thing. So we're going to utilize our 41 watt hour goal, but this time we're going to work a little bit backwards because right now, right, if you remember way back at the beginning of this presentation, I told you all that the time is specifically like we want to try to figure out the best time for this treatment, okay? So with that specifically, we're going to utilize the irradiation absorption that we are going to measure. And we're going to look at the irradiation absorption that we actually calculated earlier. That's my bad. The irradiance that you were measuring from the paper and the area of exposure. All right. And from that, you're going to get the duration of exposure. And with this, you're going to get it from each different, distance that you're actually creating. All right. And then from here, you're going to further analyze the data, right? Because I know someone mentioned earlier cost. And so with that specifically, you're going to figure out like, okay, what is the correct number of lights that I need to create to actually get a good cost? So you're going to utilize $50 as a value of cost per light. And with your design, you have to you're going to have each circle is essentially going to be a light, right? So figure out, okay, how many lights do I need? And how much is that going to cost? And is this actually cost effective per patient, or is this actually a problem that we need to address? All right. And then I'll get into this a little bit when I wrap up today, but if you're also interested in all of this, you may be also interested in like Grover's disease and like actually going into physics with light. And you may also be interested in biomedical engineering, electrical engineering, chemical engineering, but also keep in mind too that within engineering, nearly every type of engineering is involved within the space of medicine, right? Because so you need like computer engineers to actually make, like, for example, when it comes to like an MRI machine, you need computer engineers to actually, build circuit boards for the MRI machine. You need electrical engineers to actually build the wiring. You need mechanical engineers to figure out how like to get the moving parts working together, right? So it's really important to think about like with all these different types of engineering, how everybody works together and comes together to actually solve these problems. And it's really nice in that sense because it makes science really collaborative and interesting because everybody has a different perspective, okay? All right, that's all I have for you all. If you guys have any questions, let me know. Other than that, have fun today and enjoy.
Well, I want to hop in and just say amazing introduction, Erin. Thank you so much for providing the background and the instructions for our students who are, I'm sure, ready to roll and excited to get building and designing their solutions. So, sorry, just